So in order to make predictions about properties, we need to be able to predict the relative strength of intermolecular forces in compounds. So when you're asked to compare intermolecular forces in two molecules, there are some things to prioritize. First thing you should look at, as I get my pen out, is see if the molecules are of comparable size, and if they're and comparable shape. So if they're both polar and they're both about the same size, it's the one that's the most polar that's going to have the greater intermolecular forces. Okay? Or if they're both nonpolar, and you guys should be writing this down, if they're both nonpolar, it would be the one that would be bigger. So it says that's sort of the second bullet. So when molecules differ in size, the electron cloud will be the deciding factor, regardless of any differences in polarities, unless hydrogen bonding is in effect. So in general, bigger molecules have stronger intermolecular forces, unless one of them has hydrogen bonding, and then it, by default, has a higher intermolecular force. So the next couple of slides are going to look at various molecules, and we're going to predict the strength of their intermolecular forces, and then based on that, make some decisions about the properties that were on the previous slide. So just so you know, intermolecular forces are much weaker than covalent bonds, but they do have strong enough forces, or they are strong enough to affect physical properties. If you look at the difference, so this is the energy needed to break a covalent bond, or an OH covalent bond, where electrons are being shared in here, compared to the energy to break a dipole-dipole force, or the energy to break a force of attraction between two nonpolar molecules, or even hydrogen bonding, which is, compared to covalent bonding, very, very, very weak. But they are strong enough forces between molecules to affect their properties, and we're about to talk about how the strength of intermolecular forces affects the properties of compounds. So we have two molecules here, and the first thing it wants us to do is identify the intermolecular forces, and then explain which one would have the higher melting point. So this guy here, okay, so if you look at the molecule, it's relatively symmetrical. So if you drew a line here, it's relatively symmetrical. It does have this polar O here, but there is a dipole moment here and a dipole moment there, and they will cancel out. So this one is relatively non-polar, but it does have London dispersion forces. Okay, it might be a little polar. There might be a little dipole forces because of this electronegative O, but it's relatively non-polar. However, this molecule has all three intermolecular forces. It's polar, so it has dipole-dipole. It has hydrogen bonding because it has O, and then hydrogen connected to a very electronegative element. And then all molecules have London dispersion forces. So this has all the intermolecular forces. So since it has the strongest intermolecular forces, it's going to have the highest melting point. So what I would write is, so because H bonding, right, because it has H bonding, it has the strongest IMF. And as the thing goes away, previous slide, strongest IMF, so then higher melting point, and the reason why the melting point is higher is it's harder to pull the molecules apart. And the molecules have to move further apart when they melt. So please take a picture of the writing that you did on the slide to get credit. And so a higher melting point, and the reason why that is, which I want you to write, is because because of the strong intermolecular forces, it's harder to move the molecules further apart, which is needed for melting. Okay, so 1-propanol, which is here, okay, boils at 97 degrees Celsius, and then octane, okay, boils at 125 degrees Celsius. So what type of intermolecular forces occur within substance justify the difference in boiling temperatures of these two substances? So this one is an interesting one, And it's one of the ones that they wouldn't make you predict, they would give you the boiling points and then make you make a prediction. So notice, if you notice, octane here has the higher boiling point. So it's harder, or we're talking about boiling point, yeah. So that means it has higher intermolecular forces. Well, that seems strange because this one is completely nonpolar. But this one is so large that it has very, very strong London dispersion forces. It's so big, as again, this thing is annoying, that it has really, really strong London dispersion forces. Oh, this one has weak London dispersion. It does have a little bit of hydrogen bonding here, but this molecule is so big that it has such strong London dispersion forces that the forces of attraction between these molecules are high because it's a huge molecule, with a huge electron cloud that is likely to be polarized. So this has a large electron cloud, and therefore it's likely to be polarized. Now, you might not know that, but again, they told you which one it had a higher boiling point. So the only reason why this one would have a higher boiling point is that it has to have really, really, really strong London dispersion forces, even though this one has hydrogen bonding. So again, sometimes they may give you the boiling point, and you have to justify based on what you know. Alright, so here we go on this one. So again, this question here wants to know which one would have the lowest boiling point. So if we look at these molecules, and let me get my pen out again, they're relatively the same in terms of polarity. They're a little polar. They got some oxygen in them, which is a little bit polar. So again, they're sort of similar in their shape, but this one has more carbons, or is a bigger molecule. 1, 2, 3, 4, 5. When this one only has 4 carbons, or it's a smaller molecule. So this one's going to have a lower boiling point because it has weaker London dispersion forces. So then it's going to be easier to pull apart the particles here. So again, these are relatively the same in structure. This one just has an extra carbon added to it. They both have the double bond O and the O in the middle. Alright, so again, here we have, these are two formulas that have the same chemical formula, they're just different shapes. And the one that is linear in shape, okay, is always going to have the higher melting point. So remember we talked about the things that affect London dispersion forces. It's being that things have stronger London dispersion forces when they're large and straight or they're straight chains. That makes the London dispersions easier to happen. This is sort of like a cloud that's hard to polarize. So, so Y, as we write Y, and again, we're going too far. Again, so Y, so since this is and I want you to write this, I'm not going to write it. So then this is a straight chain, okay? It's easier to polarize the electron cloud, which makes it have larger London dispersion forces. And then, because it's large, they're about the same size, but it's a straight chain. And because it has larger London dispersion forces, it's harder to separate the molecules when you need to boil. And I would like you to submit this slide as well for a grade or for the homework. So if we look at these molecules, and I'm going to draw them. So here's carbon dioxide. And let me pause the video while I draw them so I don't have to make another video. I can't find my mouse. There's the mouse. So I drew the dot structures, and again, you would be expected on a multiple choice possibly to draw them yourself. And this wants to know what's true about their boiling point. So let's talk about their polarity. So this is nonpolar, and again, annoying thing. This is nonpolar, and this is polar. So we would think, okay, well, this one is going to have stronger IMFs because it's polar. But it's not only does it have stronger IMF because it has dipole-dipole, because it says dipole-dipole, Se is also a bigger atom than carbon. So it is also going to have a larger London dispersion forces. So the only force here is London dispersion forces. Well, this one here has London dispersion forces, which are actually greater than those because Se is bigger, and dipole-dipole. So because it has stronger intermolecular forces, their melting points are very different. In fact, this one's a gas and this one's a solid. So they're very, very different in their melting points, and Se2 is higher. So this question says, arrange the following substances in order of increasing melting point. So again, we want to identify the ones that are highest are ionic. So this one is ionic and this one is ionic. So now we have to think, okay, well, which one is going to have the stronger ionic bonds? And if you remember, that's Coulomb's law. And what matters first is charge and then distance. So we see that this is +2 and that's -2. And this is +1 and that's -1. So this one is going to have the first highest melting point because it has the biggest charge. So it has the strongest Coulombic forces. Okay, I would write that down. And this is going to be second. Okay, because it is also ionic, but it has weaker Coulombic forces because it has less charge. And then now we have these molecules. Water, these are both, if you drew these, they're both symmetrical and they're non-polar. And this one is polar. This one has hydrogen bonding. It's water, so it has dipole-dipole, hydrogen bonding, and London dispersion forces. So it would be next in terms of melting point. And now we have the two non-polar ones. So this is carbon dioxide. I'm leaving out the lone pairs on the oxygen. And this is oxygen. This one would have the higher melting point because even though they're both non-polar, this one would have greater London dispersion forces. So this one would be fourth. And then the last one in boiling point would be fifth. So this would have the highest. This would be the highest because it has the strongest. This one has lattice energy or ion-ion forces. Or it's lactin, a crystal lattice, and this would be the weakest or be the easiest to have the lowest melting point because it only has London dispersion forces, and it's very weak because it's a small molecule. All right, another question. So comparing these two substances below, select the true statement below. Acetone boils at a higher temperature, 2-methanane boils at a higher temperature, or they boil at the same temperature. Again, this is mostly nonpolar. So because it contains only carbon and hydrogen bonds, so it really only has London dispersion forces. This has a slightly dipole moment here. So it's polar, so therefore it has dipole-dipole forces, and it also has London dispersion forces. So it's going to have stronger IMFs, and because it has stronger IMF, it's going to boil at a higher temperature. So acetone is going to boil at a higher temperature, so at a lower temperature. So no, I have stronger, my brain needs to slow down. So it has stronger intermolecular forces, so it's going to boil at a higher temperature. Remember, stronger the intermolecular forces, harder to separate the molecules apart. Alright, so the last thing we have to talk about is equilibrium, how IMFs affect vapor pressure. And remember, vapor pressure is when you're in an equilibrium at a closed system, the molecules are going in and out of the gas phase and the liquid phase. And we've talked about this several times. So the question is, what affects the vapor pressure, or what type of molecules have higher vapor pressure? So it makes sense, based on what we've been learning, that if you have weak intermolecular forces, you're going to have a higher vapor pressure because more particles can escape. Or more particles, and you can write this down because again, I'm running out of time and I want to make another video. If you have weaker intermolecular forces, more particles, or it's easier for the particles to escape into the gas phase. So I am going to have to make another video. So order these substances in according of increasing vapor pressure. Why don't you do it and then watch the last and final video.